Hello and welcome to today's physics lecture, wherein now we shall be studying about the Lorentz magnetic force and thereafter the Lorentz force. So first of all, to understand the Lorentz force, we need to understand the Lorentz magnetic force. So it is Lorentz magnetic force. Now let us see that what Lorentz magnetic force basically tells us about. It tells us that first of all we need to understand and we need to recapitulate as we have learned in electrics. Like over there while we were studying about the electric circuits, we know that due to the passage of electrons, a current is being built up within the conductor. Likewise, the charges is basically of two types, the positive charge and the negative charge, right? Over here, the circumstances is such taken as, say for example, this is a plane, right? And in this plane, a charge is being kept as such that the charge is plus Q, say for example, right? And this charge is drifting with a velocity of say V. So V is the velocity with which this charge is drifting or this charge is moving. Now, for example, if it is as such that the magnetic lines of force is present over in this circumstance or the magnetic field is present. Now, say for example, if the magnetic force is present as such that this is the magnetic field B, right? Now, if this is making an angle of say theta, this angle is being made with the vectors of this velocity vector and the B vector or the magnetic field vector, then it is seen that this charge experiences a kind of force. First of all, this charge is drifting with the velocity of say V, and this drifting of this charge is being done when this is the scenario that here is a magnetic field. In that circumstances, this charge actually do get a kind of force that this force is perpendicular to this plane, the plane of V and B, and this is known as the force. But obviously this force is only for this magnetic field, and that is the reason why we represent this force as Fm. This Fm is known as the Lorentz magnetic force, right? So we can represent the Lorentz magnetic force as such that Fm is equals to, first of all, there is a charge, so we shall write it likewise, plus Q multiplied by this velocity vector cross product with this B or the magnetic field, right? So this Lorentz magnetic force, it states that this force which is experienced by this charge plus Q will be equal to the product of the amount of charge of plus q and the cross product of the velocity and the magnetic field vectors. And if this is a cross product and there is an angle of theta, then we can write that f of m now is equals to plus q multiplied by v b sine theta, right? So what this will be? This will be the magnitude of this Lorentz force. So we can write simply this Fm magnitude will be equal to BQV sine theta, right? Now this is the magnitude. Now how to determine the direction of this Lorentz magnetic force, right? Again we have to see that over here this is a cross product, and how to determine the direction, because this will be, the direction will be along the axis perpendicular to this plane. Simple. Use the corkscrew rule or the Maxwell's right hand thumb rule. Place your other fingers of the right hand in such a way that the curling of the other fingers indicate the angle, the direction of this angle. See, we are moving from V to B. So this will be the curling like this, right? And if this is the plane, obviously it will look like this. So in this plane we shall see that if we keep a plane like this and if we curl the fingers, we will see that the force which is exerted on plus q will be on the upward side, right? This is a three-dimensional figure. Now after the Lorentz magnetic force, there comes the concept of Lorentz force. Now, what does the Lorentz force actually implies? The Lorentz magnetic force is basically in that situation when there is only the presence of this magnetic field. But in case, in the presence of electric field as well, which we denote it as capital E, we know that the electric force that is being exerted is equals to, we should write it as like this, is equals to basically, if this charge is say plus q multiplied by E, right? And we have seen in this scenario that f of m is equals to q multiplied by the velocity vector and the magnetic vector, like the magnetic field vector in cross product. Now, if it comes the scenario that both the electric field and the magnetic field is present in these circumstances, then what will be the value of the total force? The total force, this kind of total force is known as the Lorentz force. So, F will be equals to Fe plus Fm, where this capital F is the Lorentz force and this capital Fm or this capital Fm, it denotes the Lorentz magnetic force, right? So we can simply write it as this one as replaced by QE plus this one replaced by Q multiplied by the velocity vector in cross product with the magnetic field vector. Or in other words, we could write that this F now is equals to Q taken as common from both the expression. This will be E plus V cross product with B. So this is the expression for the Lorentz force, wherein we see that both the electric field and the magnetic field is present. But over here in the Lorentz magnetic force, only the magnetic field is present. And we have seen the expression and how to deduce the direction of this force, right? So, for example, we know that the electrons drift, right? And if the electron is over here, the value will be minus E, right? So we will see this direction as minus E multiplied by the cross product of V cross B, right? In that scenario, the direction of the force being experienced will be downwards, because this will be minus of Q. It is or minus of E, right? It means that simply the direction which is showing over here, it will simply be on the opposite side. And the drift of the electron means actually the current is passing, right? So it means that if a conductor is being kept which is carrying current, right, or which is carrying electricity, which means that the electrons are flowing through it, and if that particular thing is being kept in a magnetic field of say B, then the Lorentz magnetic force will actually get applied on that conductor, and it will experience a force of magnitude BQV sin theta, where theta is actually the angle between this drift velocity and the magnetic field. Now let us check for this Lorentz magnetic force. Let us check the cases. As case 1, over here see, if this theta is equals to 0, theta is equals to 0, which implies that this Q is actually drifting in the direction of B, right? Q is moving along direction of B. So the theta will be 0 in that scenario, and it will be, the magnitude of this Lorentz force will be equals to B multiplied by Q multiplied by V and multiplied by sine 0. Now what is the value of sine 0? The value of sine 0 is simply equals to 0, so the entire expression will come out to be 0, right? So the Lorentz magnetic force in this scenario will be equals to simply as 0, which means that in this scenario, if this Q is moving along this direction of B, it will not experience any kind of force, right? Now let us take the second case. Now say for example, if this theta is equals to pi by 2. If theta is equals to pi by 2, which implies that V and B are perpendicular to each other, which means that the Q is actually drifting or moving perpendicular to the direction of B. So it means that Q is moving perpendicular to direction of B, right? And if this is the scenario, we will see that the Lorentz magnetic force that is actually exerted on this charge will be equals to BQV, multiplied by sine of pi by 2. Now what is the value of sine of pi by 2? It is equals to 1. So the Lorentz magnetic force will be equals to simply BQV, where B is the magnitude of this magnetic field, Q is the amount of charge, and V is the velocity by which this charge is drifting. Okay? Now we can see that in this scenario, actually in case 2, the Lorentz magnetic force that is experienced is the maximum, and in this scenario case 1, the Lorentz magnetic force that is experienced is the minimum. Right? Thank you.